this is actually a really great opportunity. I'm excited to do this. I was actually hoping to get a chance to go and visit there in Liverpool and do this over the summer. But obviously we know that things changed quite a bit from when I was first invited to when came time for that thing to happen. On the bright side, I think I have some new things to talk about, which are actually wouldn't have been able to explain during the originally scheduled meeting back in July. So I guess there is some. We don't talk much about the positives of COVID, but this maybe is one of them. Obviously, that's a joke. You're all on mute, so I can't hear if anyone laughs. But anyway, so I wanted to talk today about today and also tomorrow about this inferential model framework. And so I'll tell you what this means. Maybe a more informative title would be about the construction of and then the properties that we hope to achieve by within these kind of inferential models. So I have my website there is linked at the bottom. So I'm going to, all of the materials and things, so my slides are there, papers and things can all be found. Most of them are links to other places, but the papers are all there. So if you wanted to find some of these references or other resources, all that stuff is there on my website. So the context that I'm going to be talking about here today is statistical inference. So by that I mean interested in quantifying uncertainties about things that are unknown. So often these are like model parameters or maybe like future data points. But the way I want to do this is I have some data, I have some statistical models, maybe I have some other things. And the goal is to convert that stuff, that input, data, models, et cetera, into some kind of quantification of uncertainty about those unknowns. So statisticians like me, we only really learn about ordinary, like Kolmogorov style probability. And so when you think about uncertainty quantification, you immediately think, okay, this is just about constructing some kind of data dependent probability distributions on the space of unknowns. But this group, and I guess more recently, I've kind of figured this out sort of myself, is that, well, A, we know that ordinary probability is not the only option, and B, it may not be the best one. So even though statisticians are almost always thinking about ordinary or precise probabilities, there are some kind of clues in the literature that says that, in fact, ordinary probabilities may not be the right thing when we're thinking about the inference problem. So way back, Fisher had developed this idea, what he was calling the fiducial argument. And the idea behind that was to take the data and the model and directly construct what he called a fiducial probability distribution that was defined on the space where these unknowns live. And so this was Fisher's proposal and something that he fought very hard for the latter part of his career in life. This eventually lost out. So there was some confusion about, okay, what's the difference really between what Fisher was proposing as fiducial probability and what Neyman came along a few years later and said, no, we call these things confidence intervals. It really was very confusing what was the difference between them. And ultimately the Neyman's notion of confidence ended up winning. And so virtually no one in statistics talks about fiducial probability anymore, whereas almost everyone is talking about confidence intervals and confidence related things. So somehow this probability aspect created problems. And so really Fisher and others were never really able to overcome this. The other side is, so in a Bayesian framework, this is, of course is very classical type of stuff, but if you want to ensure that these Bayesian posteriors have some good statistical properties, and I'll be a bit more careful about that later, you really need to use these prior distributions that are sort of, quote, non-informative. And this really isn't something that belongs in ordinary probability theory, this notion of non-informativeness. And so it really doesn't quite make sense that you have to, or at least if you're following this argument that ordinary or precise probability is the right thing, that somehow in order to achieve the kind of properties that we want, we have to break free and go into this sort of non-informative world. There's also the fact, I mean, so Ignacio had a very nice description at the end of his presentation about sort of the timeline of these arguments. And so, like I said, statisticians mostly ignore everything there except for the Kolmogorov step. But in those statistical problems, Dempster was also thinking about ways to sort of overcome those challenges that Fisher, that were identified in Fisher's framework. And so this is in some sense where the imprecise probability story began. Not exactly, but that was a big point in time. So it's just, even though statisticians really want this to be handled within the context of ordinary probability, there's just a reason to believe that that's not possible. So then the question is, so what is it that we want to, what would be a better framework? So if ordinary probability or precise probability isn't right, then we need to try to find something different. And so this was really where I kind of entered into this work. I didn't actually know really anything about imprecise probability at the beginning. And I mean, compared to the others here, probably know very little. The question is, right, it's not just about switching from one thing to another and that solves it. It's that you have to actually say, well, what does it mean for this new formulation, whatever we're trying to achieve, what does it mean for it to work? And so when we're talking about statistical inference and uncertainty quantification, we need to say, like, what does that mean? What does it mean to work? And then naturally, once we know what it means for something to work, then how do we actually get there? What do we have to do to achieve that property? This is what I wanted to talk about in this series of lectures. So I've got it, I guess, three sort of parts to the lectures. So today is the first part, and then we'll have two parts tomorrow. So they're not, I split them up and they're not really in equal parts, but so what I wanted to do today, the first lecture, is to talk kind of about why I'm doing what I'm doing and what I hope to achieve. Then the next lecture, which will start tomorrow, will be a little bit longer. This will talk about kind of the how aspect. How do we actually achieve those things? And then, I think it's good, since this is not really about me presenting things that have been done. I actually hope that I can, get others involved. And so I think it's a good idea for me to say kind of what I think is next. And I guess one part of this is that, like I mentioned, I'm a relative newcomer to this group. So I've kind of been picking up over time in the recent years some of these notions of imprecise probability that you guys take as kind of standard. So now I'm starting to think about some of the statistical problems in this same kind of way. So I hope that at least some of what I have to say in this kind of like what's next, the last part of the lecture series, will be things that will maybe connect with you guys, and you may have some ideas about how to solve these things. And so I think this is a good opportunity to kind of share some potentially interesting open problems that you guys may know something about. So I guess first off, references. So this is the book that Marco was mentioning. So I'll be talking about some things from this book. This is mostly what part 2 of the lectures will be about. So today I won't really be referring to this. I did want to mention, so Ignacio did a nice job of including some important imprecise probability references in the slides. I didn't do that, so I only have a picture of my book, but I think it's also worth to say that I have here Wally's book, and I have this one, and I also have Mateus' book here. So I think it's more meaningful that I've actually owned these and look at them than just having pictures on the slides. So the parts 1 and 3, part 3, of course, is about sort of open questions and things like that. So I don't really have references, but I'll do the best I can. Part 1 today, this is based on some stuff that's mostly new material, things done more recently since the book was published. So I'll point you to some of these references, and I'll also have them they're on my website and they're on the slides. So I prefer to point you to things which are freely available. So I use even if things are published, I will point to the archive links, or also to the Researchers One links that Marco did mention something about. I think this is important because I want you to have access to these things, and the journals actually are not very good about making things accessible. So part of what this Researchers One initiative is about is to try to make it possible for researchers to be engaged in scholarly community in other ways besides through journals. So I did want to take just one brief moment to kind of mention is that, so one of the things that we're trying to do with this platform is to kind of integrate the various things that researchers do. So we have things about peer review and publications, conferences and proceedings, and maybe other kinds of things. So along this line, actually the quick advertisement. So our first virtual workshop held on the Research One platform is actually next Friday. So if you wanted to, you can find links on my website, but also you can see here is the link to see the conference page. And if you wanted to register, all of that stuff is there. So it'd be a real, I think actually one of my goals is that I hope that at some point SIPTA conferences and proceedings are all hosted here on the Research One platform. I think that'd be really outstanding. So one last thing before we get started, actually very important figure in the development of statistical inference actually passed away not too long ago. This was the end of December last year. So Don Fraser was, he was 95 when he passed away. So he was around at the same time that like Fisher was developing and sort of pushing for this fiducial inference, and Dempster was developing his framework. So he was around at all, you know, those times. He was, I wouldn't say that he was a supporter or sort of proponent of imprecise probability, but that he definitely recognized the limitations of ordinary probability and was trying to push folks away from just thinking, well, if I can write down a prior and I can get a posterior, then I'm done. There's something sort of missing there. And he was sort of for many years trying to push this. So he had actually a tremendous impact, in my opinion, at least on the field of statistics and also on me personally. So this is a great paper, and the discussion and rejoinder is actually really, really nice. So if you're not familiar with Don's work, I recommend that you take a look at that. I think this would be, at least some of it would connect with folks who are more in the imprecise probability community than in statistics. Okay, so then we can get started now. So what I wanted to start with, obviously, is that I'm not going to assume that you guys know all of this kind of setup. So I want to give a little bit of a background about this statistical problem. Then what do I mean by probabilistic inference? And this will really be where we define this inferential model and what it is that we're trying to achieve. So then there's some kind of property that we wanted to satisfy, and why do we want it to satisfy that property? Then the question becomes, okay, what should this inferential model, this probabilistic inference, that output, what should that look like? So should it be a additive or ordinary type of probability, or should it be something else? And if not probabilities, then what is the right way to be, what is the right type of probability model that we should use? So should it be lower provision? Should it be possibility measure? Should it be something else? So that's the question there. So then I wanted to end with what is, I guess, a relatively new result, talking about sort of this connection between general sort of frequentist inference, this validity property, and imprecise probability. So I hope that this will kind of show how important and how fundamentally important the imprecise probability framework is to frequentist statistical inference. It has, not because we're using models that are imprecise, but because this imprecision is actually essential for quantifying uncertainty in the context of inference. All right, so the starting point is that, well, we have some data, right? And so here's this data Y. This data lives in some generic type of sample space. I'll call it this bold Y. So it looks, I'm just talking about one data point, but this Y could actually be, could be vector, could be matrix, could be all sorts of things. So that it's just to keep the notation simple, but this is a very general type of object that we observe. It could be, for example, could be in the classical situation, we're normally thinking about like I have some IID observation. So this Y could be a vector of, say, n IID observations from some distribution. Okay, and so what makes these data relevant to answering some kind of questions is this model. So there's a statistical model which is being specified, and this one is simply a collection of probability distributions indexed by some parameter. So the notation I want to use here is I want to write this funny font, virtual value. So here in this formula here, that's kind of just a description of what I mean by a model. This is just a collection of distributions for Y that depend on this parameter theta, and the theta ranges over the whole, this parameter space big theta. So what's going on is that I have all of these different parameters. I just don't know which one is this special font theta, right? So this is the ordinary font. That's the one I actually want to know about. This is just a collection indexed by generic parameter values here. So my goal is to, I'm going to see this Y. So eventually Y is going to be delivered to me. So either I go to, maybe I go to I designed some experiments and I, said, okay, these experimental units are assigned to, treatment 1, these are assigned to treatment 2, and then I do some kind of a experiment and then I collect the data. So eventually I have this Y's in front of me. And so then what I want to do is I say, well, these Y are related to this phenomenon under investigation through this model. And the model is determined by this parameter. So I want to somehow quantify my uncertainty about that unknown parameter using the data that I can observe. So here is where there's some kind of departure in terms of how we approach things. So in statistics, there's basically just 2 ways to think about this. One is what's called frequentist and one that's called Bayesian. So they're very different. And so the basic idea is that the frequentist says, well, all I really care about is that I can construct some kind of procedures that have good properties. So things like I can test hypotheses, I can construct confidence intervals, and that these have good properties. So the good properties are things we'll talk about a little bit later. The other one is kind of thinking about it in a more formal sort of way. It says, well, I first have to say, what do I know about this unknown to start before I've even seen data? And then I take the data that I see and I do some kind of formal updating to get from this kind of a prior distribution to describe my unknowns or my uncertainty about that, about theta. And then I get a conditional probability distribution for this theta given the data, right? So, and this conditioning process is a formal one described by the Bayes theorem, basically just the definition of conditional probability. The fact that in statistics, we have 2 different ways of doing things with 2 motivations and can give very different answers, this I think is actually quite problematic. And what it does, it actually suggests that there's things that we don't actually understand. If there are 2 ways to solve the problem that can give very different answers, it must be that we don't really understand so well what we're doing. So I hope that the developments here can help to kind of fill this gap. So what I want to talk about today will be basically in 2 papers. So one is actually, I presented something about this at the 2018 meeting in Compiègne. So you can find this paper here. This other one is the sort of more recent things I mentioned. So this is actually very fresh. This is just I made a small revision just the other day. So this is a very new kind of results. So you can find the references there. All right, so now we're getting into a little bit of more details. So for this notion, for this idea of probabilistic inference, what I have in mind here is that, again, what we're trying to do is we're sort of quantifying uncertainty. And so how do we want to do that? The way I want to think of it is that this is going to be some kind of a function, and that function will depend on the Y, also maybe on the assumed model and maybe other things. So if it happens that I have prior information about the unknowns, makes sense that I should use that. And so that would also be part of the maybe the input to this function. And then what this function is going to do is it's going to take those inputs, the Y's, and then it's going to be a function which can take as arguments assertions about that unknown. So I'll write that as A. So this A is just some kind of a subset of that space where the unknowns live, this theta parameter space. And then I'm going to return a number, let's say between 0 and 1. And what this is supposed to do is to represent the degrees of belief about that assertion A, given the data that we have, the model we assumed, etc. Okay, so to sort of formalize this function, so I found this term capacity was in the Sebastian and Didier's chapter of that imprecise probability intro book. So I like that word, so I took that here. So capacity gamma, this is just a set function that takes it takes these assertions as input and satisfies these very basic properties. So to the null set I assign nothing, or assign 0, and to the full set I assign 1. And then it has this monotonicity property. So I think Ignacio was calling this one just a lower probability was the name that he was using for this. And so it just says that if one set is contained in another, then the capacity should assign a higher value to the bigger one than it does to the smaller one. Okay, so this capacity is not really so informative. It's sort of like so flexible that you can't really do anything. So we have to talk about how do we kind of add some things to this. But anyway, so here is a definition of inferential model. So this inferential model is simply just a mapping from the data model, maybe other inputs to some data dependent capacity. And it does this. It says, so for whatever assertion I want to use, this here, this lower bar, that's kind of an indication of what kind of object this will be. I put this lower bar here. So this lower bar pi YA represents the data analyst's degree of belief about A given data model, etc. So I don't know, I'm not able to see if there's comments. Am I looking at the wrong place? So maybe there are none, and that's why I can't see them. But
Ignacio just said that he calls it lower probability. That's, I mean, it was just a comment on what.
Okay, sorry about that. Is there some way that I can see these
shots? So if you go up in your screen, you should see a green bar with options, usually.
You have to exit full screen first to be able to see.
No, you don't. You don't have to exit. I don't think.
Put your cursor at the top.
Well, maybe if there's comments, you can yell at me, and then I'll
yeah.
Because I can't see anything except for the space on the side. So, okay, sorry, but yeah, if there's comments, maybe just yell out. All right. Okay, so I'm just copying the definition is there again. All right, so I mentioned about this. So ... is just to say there might be some other inputs, for example, like a prior distribution. Maybe not a full prior, could be some partial prior information about some features of the unknowns, these kind of things. So Ignacio also just talked about this notion of a conjugate, or I'm using here the word dual. This is just, you can get a corresponding pi upper bar using the 1 minus pi lower bar of the complement. So it's possible here. I mean, I'm not ruling out the possibility at the moment that that lower bar and upper bar are the same. But so they may not be distinct, but we'll see that they actually will be. Otherwise, I wouldn't have put the bar there. So this upper bar, the way I'll think of this is it's representing plausibility of this assertion A given data model, etc. So there's all kinds of different ways that you can do this. I talked briefly before about Bayesian posterior distribution. There's also fiducial and confidence distributions. Generalized Bayes could be, there's different definitions of generalized Bayes, but I know of what described in Wally's book. This also produces one of these things, data dependent capacity. And then Dempster has more recently talked about sort of formulating his thing, not in terms of belief in plausibility functions, but these things he calls PQR. So P would be the belief, and then P plus R is the plausibility. And so he does this, suggests this kind of decomposition into a triplet. And so what that means is that the Q is kind of like a belief against, and R is like a don't know. And so P plus R represents plausibility, and P represents belief. But there may be lots of other things. I just picked these as just some examples. So the point is that, well, if there's so many of these examples of this, then it's sort of too vague of a definition to actually be useful. So what we have to do is we have to kind of sharpen our focus and say, well, I need to introduce some kind of constraints so that the thing I get out, this inferential model that I get out of this process is actually good for something. So before we can say what it means to be good, we have to talk about what do we want to do with this thing. So one thing that we don't really need this heavy machinery for is to produce a point estimator, or to test a particular hypothesis, right? So there's other ways that you can get at this that are maybe easier. And so I don't really need this, to work so hard to get an estimator or to test an isolated, singular type of hypothesis. I can just do those things directly. So the reason I would want to get this inferential model is actually for the purpose of uncertainty quantification, that I actually would consider maybe various different kinds of assertions, and I'd like to be able to plug them into this function and then use that information that comes out to kind of quantify my uncertainty, to describe my degrees of belief. So what I care about actually is this mapping that takes assertions to their this capacity, lower probability. So one idea is you could say, okay, I'm going to tighten this up by saying that this lower probability should be coherent. right? That's definitely is one possibility, and Ignacio talked about this kind of thing. The statistics problem, though, has some other side to it, which is not just about sort of being internally consistent and like protecting myself from sure losses in some kind of gambles. There's, I don't want to call it objective, but it's sort of a non-subjective type of element. And so there's this basic principle, which is how you would try to use this type of output, is that when we're talking about inference, right, if I would assign some relatively high degree of belief to some assertion, then the only thing I can really do is then to infer that that thing must be true, right? That would be the only thing that this would be useful for, is to assign those degrees of belief, and then to the ones that we assign high degrees of belief to, we infer them. Okay, so now in this context, we have there's some parameter that we don't know, and so an assertion about that parameter is either it's true or false. Okay, so now if I'm looking at using this kind of principle, then of course there's a chance that I make some mistake. And so those mistakes may have some bad consequences. So by mistake, I mean the assertion is actually false, but I end up assigning it high degrees of belief, and so my inference is wrong. So an idea would be, can we impose some kind of constraints on this thing so that I avoid those bad outcomes? Okay, so obviously it depends on the data that we have, right? This little y, so that's the observed data, and I don't have any control over the data. So I get what I get. So I can't be sure that on every possible instance where I try to apply this type of procedure that I'm going to avoid a bad outcome. But what I can do is I can require that these bad outcomes are not systematic, that I can prevent these from being, I can prevent systematically bad outcomes. So what do I mean by this? So remember, what we're interested in is this property of the function, or we're interested in this function that takes assertions to their degrees of belief. But when we're talking now about these kind of properties, what we care about is the function that takes the data to this capacity. Right, and so what we can say about those things is we can require that satisfies a property like this. So what this is saying is that if the parameter is not in A, so this makes A a false assertion, and if Y comes from this distribution with parameter theta, so this thing together here basically says that it's a false assertion. So this kind of pair together says it's false assertion. So then these degrees of belief that's assigned to that false assertion should tend to be small. Right, this is how we can avoid these sort of systematically bad outcomes, is by requiring some kind of property like this. So this will get more precise as we go, but I like this message that comes in the paper by Nancy Reed and D.R. Cox. This was, I think, a few years back, 2014. So they say they're talking about maybe a different context, but I like this particular message here. It says that it's unacceptable if a procedure of representing uncertain knowledge would, if used repeatedly, give systematically misleading conclusions. So this is the thing that I'm trying to achieve, is to sort of avoid these systematically misleading conclusions. All right, so then now we come to, I sort of said, okay, first there's this objective of trying to construct a capacity or lower probability that represents degrees of belief. But now I want those degrees of belief to be reliable, in the sense that I won't tend to give systematically misleading inferences based on them. So I have to define now, how do I sort of more formally sort of protect myself from these systematically bad outcomes? And so the definition is here. So I say that this inferential model is valid if you can take any assertion and you can take any of these kind of thresholds alpha, and then you look at this probability on the inside there. What this is where I'm assigned a belief to that assertion, and the assertion happens to be false because the theta is outside of A. So theta is outside of A, the assertion is false. This is an event where I'm assigning relatively high probability to that false assertion. And so what I want is for that to be a rare event, that I assign high probability to a false assertion. So this there's some connection obviously between this cutoff and this cutoff, but what this is saying is that I'm preventing those bad outcomes, which are where I systematically assign too large a belief to false assertions. So you can ask questions about why those particular thresholds. That's definitely is a reasonable question. I think one thing I want to make clear is that it wouldn't make sense for this number here it could be something different than 1 minus alpha, but it wouldn't make sense if it depended on Y or if it depended on A. Depending on A, well, depending on Y seems strange. I think that maybe is clear, but depending on A, you could ask, well, why would you not allow it to depend on A? It would be like, you know, if you were coming up with some kind of measures of uncertainty, and if, you know, think about like the weatherman. So the weatherman is giving you some kind of, you know, these percentages of rain and other kinds of precipitation, that somehow the threshold that you would use might depend on whether the assertion was about rain versus snow. So we're going to treat these degrees of belief, these probabilities, as we're going to treat them the same no matter what kind of assertion we're talking about. So it wouldn't make sense for this to depend on the assertion. It also doesn't really make sense to depend on the data, because I'm never going to consider the data itself when I sort of judge whether this is a strong support for an assertion or not. That's going to be something that's sort of free of the data, free of the assertion. So you still could imagine some function of say, of alpha that's a decreasing function. I don't know if there's anything that makes any more sense than this. So I think we could consider other things, but I don't see why this is particularly a restriction. You'd have to say what it is in advance, so then you might as well say it's this. So a couple other questions I do want to talk about, but not right now. I'll postpone to the third lecture. So that is, oh, there it is. Okay, sorry, I kind of see the chat now. I don't know what's happening. Oh, I see.
Marius, do you want to try and give it a go? Your question?
Sure, yeah. It's maybe too technical, but something I wonder when I see this formula is, instead of having like less or equal than alpha, you could say, you could add a limit for alpha to 0 on the left-hand side and require that that limit is equal to 0. And that's obviously weaker than what you have. But I'm wondering
Sure.
if that's enough, or is that too weak?
Well, I guess I don't know. I mean, what we ultimately want to do is have kind of like a fixed, I mean, at least in some of the results, what we have in mind is maybe I can compare these lower and upper probabilities directly to an alpha, and then use them to make some kind of judgments. So then if alpha is moving, that maybe complicates things a bit. But I mean, I certainly would consider the possibility that there are other, maybe slightly more general ways of describing this.
Right. Okay. Yeah.
And so I mean, I think maybe we could wait till the part 3 and we can talk about that. So I mean, definitely there's some added flexibility we could consider. And so then the question is, what is kind of the consequence of that? Yeah,
but you want to consider specific values of alpha in specific applications, and that's why you're going with this. Is that? Yeah. All right. Thanks.
Sorry, let me try to. Okay. Now I can see the chat at the same time. Okay, sorry. Yeah, right. All right. So a couple of consequences of this notion of validity here. So one is that because I'm requiring this to be satisfied for all of the assertions, so then I can just replace this definition with I can replace the capacity in that definition with its dual. So then I can rewrite everything in terms of this, the corresponding upper probability here. So that's an easy thing to do. You can see it just sort of swaps you just basically are replacing the definition of A with A complement, and then the same kind of definition. Okay. So this is one thing, is that because it's for all assertions, we can treat the lower and upper probabilities basically in the same way. So the other one is I'll write it here as a theorem, because I think this is sort of worth highlighting. So one is that if we can satisfy this validity, then we can immediately get frequentist procedures that have error rate control. So one is that if I wanted to use, for example, this upper probability at the assertion, I could use that for as kind of a measure of, you think of it as like a p-value basically. And so this would be like the p-value for a test of whether this hypothesis theta in A is correct. And so the rule would say, let's just reject that hypothesis if this upper probability is smaller than alpha. Right, then this has the property that size alpha, that it's a size alpha test, meaning maybe you've heard about, like, so in type 1 error, it says that the type 1 error is no more than this level alpha. So these are things that whether you're Bayesian or you're a non-Bayesian, these are things that statisticians care about, is being able to construct tests that have good properties. Similarly, you can, a thing I'll call here the plausibility region. This will just go to singleton assertions and then collect all of those corresponding parameters that have plausibility to the singleton, at least alpha. I maybe need to have this less greater than and not greater than or equal. But anyways, so this is just saying, okay, I can collect all of these parameter values which are sufficiently plausible. And then that collection of plausible values has the property of being a confidence region. So that is that as a function of the data, this collection will miss the true parameter value with parameter at most, or with probability at most alpha. Okay, so we have this kind of control on the error rates that comes out of this validity property. So not surprising, because the validity property is it has built into it some kind of frequentist notions. So the point really is that, well, there are things that we would maybe like to do with this output, for example, to do tests and to construct confidence regions, and validity gives you the properties that you want directly. So of course we get some nice properties. I think that this is a strong condition, and I'll save for the next time, or for tomorrow in the second session tomorrow, about kind of ways that we can relax this. I will say a few things about just sort of brief comments about this at the end of the lecture today. So then the next step, okay, so I have this target of validity in mind. Okay, so we could consider other sort of variations on this definition, but let's say for now we'll take this as our target. So then the next question is sort of, what kind of properties, mathematical properties, should this the mapping from assertions to lower or upper probabilities be, so that I get something that's consistent with this validity condition? So it's not guaranteed that any kind of mathematical structure in that mapping from assertion to lower or upper probability would be consistent with validity. It may be impossible, actually, that if you don't, if you're too restrictive on how this can assign degrees of belief, it may be inconsistent with validity. So that's here the question is. So first is, could we do this with just ordinary probability? And then the follow-up question is, of course, if not, then what would we do? So this was an example that was, I guess, presented to me, I guess probably now a couple years ago. Michael Balch, I'm not sure if Michael's here, but so he contacted me and was kind of telling me about this satellite problem. And so Scott is also is connected to this. So you see here at the bottom is Michael and Scott's name here. This was a problem that kind of was brought to me by Michael, and then I got to know Scott sort of through this kind of collaboration. So in this particular problem, the idea, well, what the researchers are interested in is making sure that satellites that are orbiting Earth don't collide with each other or other kinds of things. So they call this satellite conjunction analysis. And so what's going on here is that they collect data on sort of the position of the satellites, how fast they're going, kind of acceleration in these various kind of directions, and so they have these sort of these measurements like position, velocity, acceleration, these kind of things. They also have some physical models like coming from the physics. They have some statistical models, and so what they do is they kind of put all this stuff together and they calculate a thing they call the collision probability. So this is basically is a kind of a subjective description of their belief that the satellites are going to collide. So this is done at kind of like a particular snapshot in time to say, okay, at this time, what's the chance that they're going to collide? And so then they kind of want to sort of do this so that they have time to make some adjustments if they believe that they will collide. Okay, so what goes, I mean, it's really pretty clear is that if you calculate this collision probability, and if the collision probability is low, then you assume that the satellites are fine. So you judge them to be safe. Otherwise, you try to do something. So they can shoot off some kind of, I guess, some rockets or something to sort of change the trajectory so that they might, then the two objects, the satellite and the other satellite, or satellite and some garbage, that they don't collide. Okay, so what was surprising to me, I guess Michael was telling me about this, in that so there's an unusual phenomenon that's called a probability dilution in this satellite conjunction literature. And so they say, I guess a one-line summary of this is that, well, if the data are noisy, then the non-collision probability tends to be large. Okay, so this is problematic because you kind of don't have control over how high of quality your data is. And so you may end up with data that just happens to be noisy. And Michael says in this context, it's actually the data is very noisy. And so then what you're going to do is you're going to calculate this collision probability and then use the magnitude of that thing to decide whether you think the satellite is safe. So if it turns out that just having noisy data makes the non-collision probability large, it means that you're thinking that the satellites are safe when they may not be. Right, so this non-collision probability is putting you in kind of a dangerous position because of this probability dilution, that noisy data makes this probability sort of artificially large. So I just have a few pictures here to sort of show you what's happening here. So I have in these pictures, I mean, this description at the top doesn't really matter. So in the pictures, what's happening is that I have the sort of log of this measure of the noise. And then on the vertical axis is the non-collision probability as a function of the sigma, like the noise, and also of the data. So the data here, I show you 4 different examples of different data sets. These are just summaries of the data. But what's happening is that, I guess the main point of these 4 figures is that as you move to the right in each panel, it eventually goes up towards 1. So this is that probability dilution phenomenon that says, well, if the data are noisy, you just tend to believe that the satellite's safe. Okay, so these are just 4 different data sets, but the same thing happens really no matter what. So this is sort of independent of what the data says. If there's enough noise, then you think the satellites are safe. All right, so this was sort of thinking about this question and kind of how it's related to the way you, I guess, assign degrees of belief to these assertions. And so they're using this kind of notion of probability. And so we thought, well, okay, perhaps this is a more general kind of phenomenon that's not specific. I mean, it doesn't make sense that this would be specific to this satellite collision example. So you could sort of formulated this idea about what we call the false confidence. And so basically the definition of false confidence is that there's hypotheses that tend to be assigned large probability even though the data does not support them. So then it was, okay, how general might this be? And so this was a work from back in, I mean, probably was done in 2018, but then eventually was final in 2019. So this is what we call here a false confidence theorem. So it says like this. So it says, let's suppose that I have, let me call it pi sub y. There's no bar here because I want to emphasize that this is actually just an ordinary probability. So this is an additive belief that's defined on that parameter space, depends on the data. So it's maybe through a Bayes update or maybe through a construction of a fiducial distribution, these kind of things. So all different forms, but as long as it's an additive at the end. So then I can find any of these 2 thresholds. So there's an alpha threshold, which is related to the previous alpha, and then some other t threshold. So these, this is just saying that I can find a pair of numbers, alpha and t, such that, or let's say, sorry. So for any pair of alpha t that I pick, I could take anything, then I can find some assertion with the following 2 properties. One is it can contain the parameter, but it will tend to assign relatively large probabilities to that false assertion. This is just saying here's a false assertion which has degrees of belief assigned to it which tend to be not small. Okay, so obviously how impactful this is depends on the magnitudes of these t and alpha and so forth. But this just says that it's not possible to achieve that validity condition with something that's additive. So that's the false confidence theorem says, I guess I have it here on the next slide, is that there's always going to be false hypotheses that tend to be assigned high probability if your capacity is an additive probability measure. Okay, so if what I care about is achieving validity, then it can't be done using an inferential model whose output is an additive probability measure. Okay, so I'll say a few more things about this false confidence. I'll save that stuff for the end of the lecture today. Okay, so I wanted to maybe pause here for a moment. Obviously, if you have questions at any time, you can type something into the chat here. Yeah, I wanted to pause and just to sort of emphasize here. So remember, what was the first question that we were interested in was what kind of mathematical, we're interested in the mathematical structure that this mapping from assertion to lower or upper probabilities needs to satisfy in order to achieve this validity condition. And validity was sort of about reliability of these degrees of belief measures from a statistical point of view. So question is, what kind of properties or what kind of a structure does this need? And so this first question was about, can we do this with ordinary additive probabilities? And so what the false confidence theorem says here is that no, is that you can't achieve this, you can't achieve validity using ordinary probabilities. Okay, so this I think is, I don't know how much of this you folks are familiar with, but this to me, really sort of changed things. It's that we really need to be considering imprecise probabilities in the statistics context, that it's really not right for statisticians to be ignoring this and saying, well, everything can be handled using ordinary or precise probabilities. So I also wanted to kind of follow up with just a picture so that you can kind of see what's going on here. So this is a super simplified version of that problem. More details about kind of exactly how these calculations are done is in the paper with Michael and Scott. But here's just a quick illustration. So if I think about that assertion as like the satellites not colliding, so then how can I kind of summarize this false confidence sort of notion? It says that, let's think of this, the probability of non-collision. Let's think of it as a function of that data. Okay, and so if I think of it as a function of the data, it's a random variable, and that random variable has a CDF. So what I want to do is I want to look at that CDF when it happens that the distribution of y is such that there is going to be a collision. So this is like they're on a collision course, that there's really no difference in their positions at the time of when they're going to be neighbors. So then I look at what is the CDF, what kind of form does the CDF have, and it tells us basically what kind of random variables we can expect these to be. So what's going on here is I have three different noise levels. The black one is the least noise and green is the most noise. But I think the sort of main takeaway here is that when the noise is relatively large, like the green line, then the CDF is pushed way over towards the right. Okay, so what does it mean if if a random variable has CDF pushed way towards the right? It means that it's always large, or virtually always large. So this is like a more than 0.8 is really the smallest that thing can be, and then it's somehow between about 0.9 and 1. So this is saying that it doesn't matter what the data is if you have it doesn't matter what the data says. It says that this will just always be relatively large. And so if you were to use that kind of basic principle and say, well, I'm going to compare my lower probability, which in this case is just a probability, to some threshold, and if it exceeds that threshold, then I'm going to infer that assertion. You would never set the threshold higher than 0.8, right? So it's that you would just always make wrong conclusions here. So that's the sort of the false confidence in action. You're just systematically, you're going to be making wrong conclusions in this case. Okay, so then I guess the next question is, so what I just showed you was basically kind of how satellite collision, this collision probability calculation is basically a Bayesian calculation. So it's starting with something like a prior distribution and doing some updates. There's other ways that you can represent this, but that's basically what's going on. And you could say, okay, well, if maybe we shouldn't start with something that's essentially a Bayesian type of approach if we were really trying to achieve some frequentist properties. So let's maybe think more directly about how might we go from frequentist things to uncertainty quantification about the unknowns. All right, so I mean, this is probably too condensed to really be able to sort of grasp it, but virtually anything that you know about statistical procedures that have good properties, they come from this kind of calculation, or this sort of construction. So you define some kind of a function that's takes as inputs a data point and a parameter, and then here I'm just going to say that let's say that this that t of y theta, this one is big if y and the distribution that depends on that parameter somehow don't agree. So it's like if y is kind of an outlier with respect to this distribution, then t will give a large value. So examples of this are like if you know about the t-test. So the t-test would do something like calculate the sample mean based on data, subtract a hypothesized mean, and then do some standardization. So if it turns out that the sample mean doesn't look like the hypothesized mean that you used in that calculation, then the numerator would be big, and then therefore that statistic would also be big. So this is basically what's going on inside of a t-test, or like the f-tests in regression, those kind of things. And so then you would define some function, which is basically the CDF, or the survival function of that random variable. And then because of based on these ordinary or typical standard properties of probability, then that thing has a uniform distribution. And because of this uniform distribution, now you know how to set thresholds and construct, define sort of critical values so that the tests have control on type 1 error and so forth. So all of those things that that's basically some kind of standard kind of textbook statistical procedures, they all come from this. They maybe don't tell you that in those books, but this is what's going on behind the scenes. So once you have this thing, you can use it to carry out tests and confidence regions in a fairly natural way. So you have this h of t function here, you can treat that like a p-value. And so then if all of the parameters in the hypothesis are sort of implausible, then you reject that hypothesis that says the assertion is true. You can also collect all of those plausible values, all those parameters that give you plausible, all of those parameter values that are sufficiently plausible based on this like h of t calculation, and that will give you a confidence region. Okay, so this is what's going on with frequentist approach, is that you define some kind of a function like this, and then through some nice properties of that function, you can construct these procedures. But this is not uncertainty quantification, at least not in the context that I'm thinking. So all these are giving you p-values and confidence regions, not giving you degrees of belief for on the parameter space. So how might you convert these things into this inferential model that hopefully would be valid? So we already know that they can't be probabilities, but I think it's good to sort of see how you might convert these into probabilities. Here is a way that you can think about construction of confidence distributions or fiducial distributions. So these are the difference between these is kind of hard to. I don't know that anybody really knows a good way to distinguish these. It has more to do with how you construct them, not the actual output. These are attempts to define probability distributions on the parameter space that have certain kind of frequentist properties. And so that it somehow is related to those frequentist notions on the previous page is maybe to be expected. I don't know that I'm not sure I've ever seen it written this way. I thought of this as I was preparing these slides. So this maybe seems too brief to be to understand, but this was the way I was thinking about it as I was writing here. So a way to think of this is that, okay, I'm gonna go back to that h thing, right? So I can still define this h function, and I can still think about the h function applied to this statistic t. But now let's think about the theta as random, like as a random variable with some distribution. So then a way to understand what this fiducial or confidence distribution, what they're doing is that they're trying to find some distribution for theta that depends on the data, such that if theta has that distribution, then that statistic thing, h theta, now treated as a function of theta with y fixed, that it also has uniform distribution. So this is pretty heavy, so I don't expect that this is easy to process. But this is a way to think about what these fiducial and confidence distributions are trying to do, is to sort of match up those properties that the frequentist has over here, right? That this is uniform as a function of y for fixed theta. It's an attempt to try to do the same thing, but now as a function of theta for fixed y. So you have to be clever in how you can construct this thing so that this property holds. So if you can do it, now there's maybe a way to make some sense out of this, is that if I was imagining that there was a confidence region for parameter, let's call it this C alpha y. I think I called it that over here. So then what this is going to do is that this is going to assign 1 minus alpha probability. This confidence distribution is going to assign 1 minus alpha probability to that confidence region. So this is like in the early stat courses, the textbooks say something like, well, you can't interpret a confidence interval as one that contains the true value of the parameter with probability, say 1 minus alpha. So that they say that's not how you can interpret the confidence interval. Here I'm saying that this is what you can do. So you can construct that particular probability distribution so that that interpretation makes sense. All right, so now I can do this, right? So I can construct this kind of probability distribution that satisfies this. So let's, maybe not always, but let's say that I can. What goes wrong? And so the point is that that probability calculus requires a lot, right? So that somehow I can do all this integration and that this has some impact on how those belief assignments are made. But the point is that this probability calculus isn't designed to preserve those properties in this mapping as a function of y. So you can't expect that those things will still be there after you've done things like integration to a margin, things like this. So you lose some of these, the frequentist properties when you do the probability calculus. So when you marginalize or when you do these various kind of probability calculations, they're just not designed to be preserved using these operations. So here's another example of this, just to, because I want to follow up on this one a bit later. So something that's maybe different about this one here is that I'm sort of very specifically talking about kind of a marginal inference problem where there's some feature of the full parameter that's of interest. So a relatively simple type of model. I just have two observations from a normal distribution and they each have their own mean, but the variances are the same. So I had just a mean theta1 for y1 and a mean theta2 for y2. Independent variances are both equal to 1. So it's a simple kind of problem. This is one where there's really no doubt about what a fiducial or confidence distribution would be if you were going to construct one. It's just replace the theta with the y. So this is, you can check that if you, it takes a little bit of work to sort of formulate the, what this t statistic should be. So, well, not a statistic, it's just some function. This should be the, in this particular context, you could take it to be the, so you have a y1, y2 vector and a theta1, theta2 parameter. So you can just define like the L2, square L2 norm between these two vectors as t. And so then that thing has a chi-square distribution under when the data is normal. It also would have a chi-square distribution if the parameter was treated as normal. So there's some kind of symmetry there. And so through that kind of, from that reasoning, thinking about this type of definition is how you can get to here. Okay, so I have this data-dependent probability now that comes through this confidence distribution construction. So it's in some sense defined to have good frequentist properties. That's what the thing is supposed to do. So now my goal maybe in this case is to, I want to quantify uncertainty, but not about theta directly. Maybe what I'm interested in is the ratio of the theta1 to theta2. Okay, so I might imagine some kind of an assertion like this one that says, I think that ratio is less than or equal to 9. Okay, so I just picked these numbers. Okay, I forgot to define. So this phi is supposed to be the ratio theta1 over theta2. So in this case, the ratio phi is equal to 10 because 1 divided by 0.1 is 10. So now the assertion here says less than or equal to 9. The truth is 10, so it's a false assertion. So what you would expect is that the probability assigned to the false assertion would be relatively small. So maybe it wouldn't be small, but it shouldn't be large. I guess that's maybe a way to think of it. So let's see. So this is the same kind of picture as before, is that this is looking at the distribution, the CDF of that random variable pi y of a when a is the false assertion. So this should be a small or not a large number, but what you see here is actually it tends to be quite large. So this is again another instance of that false confidence, but it's coming from something which was already kind of defined or designed to be to have good frequentist properties. So somehow using this kind of a more of a Bayesian sort of thought about kind of updating prior beliefs and whatever those prior beliefs mean, doing that kind of updating can lead to false confidence. Starting something that sort of is designed to have good frequentist properties, converting it into an inferential model that returns ordinary probabilities can also get you into trouble with this false confidence. So obviously we're not obligated to use things that are additive. So this I think was really sort of the point where I started to think very differently about things, was that I only ever really learned how to do things that returned additive type of inferential models. So this was where you're giving out probabilities as output. And so this was always sort of what we were trying to achieve. And then, eventually we just found, okay, it just can't happen. And so then you say, okay, well, if I can't achieve it using additive probabilities, then I have to do something else. So then we kind of start thinking about, okay, well, what do we think maybe is going on here? And this actually isn't in chronological order. So it wasn't until later that I sort of thought about the kind of manipulations that we do in statistics when we're thinking about things in a frequentist way actually are very different from what we do, very different from probability calculus. So we would never do anything like attempt to integrate a p-value. I mean, that doesn't even really make sense, but like there's definitely no notion of integration in the frequentist type of thinking about how you would maybe manipulate p-values or confidence regions. There's nothing at all that's sort of consistent with integration operation. Okay. So if you start to think about what are the kind of operations that are appropriate when you're dealing with these frequentist things like p-values and confidence regions, you start to see something emerge, like there's some sort of a pattern and it's related to some of these imprecise probability notions. So I think the easiest way to see this is if you start thinking about marginal inference. So like where we're interested in not the full parameter, but in some feature. So like I'm calling this just a generic phi represents some low dimensional feature of the full model parameter. So example of this would be like in a normal distribution problem, maybe I care about the mean and not about the variance. So then my feature would just be the mean, or maybe the theta would be the mean and variance pair, and then the phi would just be the mean. Other things that are more complicated, actually both the satellite collision and this Feller-Creasy, the ratio of two means, these are marginal inference problems. And so very often these are the things that we're interested in. There might be a very high dimensional full parameter, but we have very specific questions that we would like to ask. So very often the goal is to quantify uncertainty about this feature of the full parameter. So if we think about how you might do this in an ordinary sort of just, I mean, if we were just saying, okay, I'm a frequentist, how would I deal with this? What you might do is you define a p-value for a test about just a point null. So that means that theta is equal to this particular, so this true theta equals some generic value, other theta. So now we could think of this as a function of that other theta value that depends on data. Okay, so now if I'm talking about a point null, the same kind of a single point about this feature parameter, this is actually what would be called a composite null about the full parameter. So there's like a set of full parameter values that correspond to this particular value of the interest parameter, this phi. Okay, so if I wanted to do a conversion of the original p-value to a p-value about phi, this is the standard way to do it, is that you take that thing which was a p-value about theta, and then you maximize it over all of those theta values that give you this particular value of the phi. Right, so this is a optimization problem. So there's no integration here. You do this by maximizing. Similarly, if you were going to construct some kind of a confidence interval for this, or confidence region for this feature parameter, what you shoot. Okay, so there's a missing thing here. So what you would do is you would find the maximum value of this, of that p-value for theta corresponding to a given value of phi. And if that thing exceeds some alpha level, I forgot the alpha there. So if it exceeds this alpha level, then it goes into the set. If it's below the alpha level, then you exclude it. Right. So these are things that you basically come up as sort of common sense ways of manipulating the p-values. And the reason why they're common sense, it's not really because they're common sense. It's because these are the operations that preserve those frequentist properties. Okay. So what's happening here is that there seems to be a very natural sort of sense, notion of doing this supremum operation on p-values. And this shows up in not just, it shows up in here and in other various kind of places. And so this optimization, this supremum operator is what preserves frequentist properties. Right. And so we saw a little bit of it earlier today with Ignacio talking about these possibility measures. And so this notion of optimization, maximizing, is actually a familiar one in the imprecise probability world. And so it's maybe not a coincidence that this type of operation is right for preserving frequentist properties and also shows up in one of these common models of imprecise probability. Right. So here's actually a very easy way to do this construction to get to take a frequentist procedure that generates for me a p-value and construct from it a inferential model that satisfies validity property. Okay. So I just define some function that has that property of a p-value. It doesn't have to be a p-value that you know, it could just be any kind of function. And the property that it needs to satisfy is that if data comes from this distribution where theta is the true parameter, then this function of y and theta has to have a uniform distribution. If you can find this, and you know, that's what we were talking about back here. So all of those kind of standard statistical procedures are based on this idea. So we can easily just apply that idea to get to here. So all of those familiar things would satisfy this first part. Okay. So then all I have to do is that if I can ensure that there's this kind of supremum property is met, that there exists some parameter value at which this p-value assigns you know, value 1, and that this is true for every y. It doesn't have to be the same theta, but I have to be able to satisfy that for every y. Then what I can do is I can define this upper probability through the optimization. I just treat this pi y here, little pi, like is it called, like a possibility distribution or plausibility contour. There's maybe lots of different names for this. So then I just do this operation of optimization and I define my upper probability in this way, that it's just maximize over that assertion A. And then that's going to give me a number. That's the number I return as my upper probability for A. Okay. So I don't have to tell you guys about this, is that this form is actually a very familiar one. It corresponds to a constant plausibility function or possibility measure, maybe some other kind of names. And so interestingly, you can immediately get the proof of validity from this, because through this optimization step. So what we know is that we can control this distribution for a fixed theta. What we don't know is that we can control it for a set of thetas. But through this optimization means that if we can control it for the truth, then we can control it for any set that contains the truth. Right. And it's just from here is that if theta is in there, then this thing, upper bar, is just the maximum. It's a supremum. So then this if this is smaller than alpha, then so is this one. And this one has already that kind of property, so that this event has probability less than alpha from the uniform distribution. So this is all super simple, is that all I have to do is take a thing which has this kind of properties that p-values satisfy, and I can construct a valid inferential model through this consonance type of procedure using possibility measures. So I don't have any formulas here, but just to show you what's going on is that if I go back to that Feller-Creasy problem, the one about the ratio of means. So there we saw that what that confidence distribution was doing was just piling up all the mass near 1. So basically always assigning large values to the false assertion. So that was sort of problematic. Here, if I do the same thing, but I first calculate this I find this p-value, and then I use consonants to construct my upper and lower probabilities. So then I can do the same kind of comparison. So this red line corresponds to my lower probability under that consonant structure. So this is basically the necessity measure like Ignacio was talking about today. So then we look at the distribution of this necessity measure and compare it to that for the ordinary probability. And so what we see is there's this diagonal line, and that's really sort of the cutoff. And it says that if you're above the diagonal line, you're valid. If you're below, you're not. And so here the red line is clearly above. So we've achieved that validity property as I sort of said we could. So this is just kind of confirmation of that theory. Okay, so in some way, the answer is clear, is that if I take, if I start with something that here I've kind of described it a little bit differently. I said that, okay, coverage is kind of related to that frequentist properties. And if I try to combine coverage with additivity, I miss this validity property. It can't happen. But if I take that coverage probability property and I combine it with this notion of consonance, right, which is to construct basically a possibility measure on the parameter space using that thing which has the coverage properties, then I can get the validity property immediately. Okay. And there's really no cost to this, because all I did was I took the thing which was a standard kind of frequentist type of concept, this basically the p-value, and then I just did something different with it. Instead of trying to construct a probability distribution, I constructed a possibility measure, and just by changing how I attack this problem, I can easily achieve this validity property on the one hand while I miss it on the other. So I think there's really no cost to this. I think it's really quite straightforward. It also sort of highlights that, well, there's something about imprecise probability lurking inside of these frequentist ideas and frequentist methods anyways. It's sort of always been there. Interestingly, it turns out to be one of the ones that was towards the very top of Ignacio's diagram of what's like complexity of these different kinds of imprecise probability models. So on the one hand, maybe that's bad because, you kind of say, okay, well, there's some, the structure that it has, I guess, costs in terms of its flexibility. But the other side of it, which I think is actually the benefit, is that it's one of the simplest ones. So being one of the simplest ones means it's relatively easy to use and to compute and so forth. So I think this is actually is pretty exciting. At the moment, I can't claim that this sort of coverage plus consonance is the only way to get there, in the sense that the only type of imprecise probability model that can satisfy this is a possibility measure. That I wouldn't claim that at the moment, but that is the direction that I'm leaning. I think there's somehow something fundamental about that possibility measure properties and the frequentist properties that we'd like to be able to achieve. So there's I guess another side to this, which is not just about about mathematics. There's something kind of else about kind of understanding what it is that we're doing as statisticians. This maybe is something that you've heard about. I mean, recently there's been lots of sort of complaining about p-values, and p-values don't do this and don't do that, and so we should ban them. And I mean, it's in some sense this is kind of absurd, but I think ultimately it's trying to find good ways to interpret what these frequentist idea, what are they communicating? How do we interpret this? How do we communicate what those things mean? I think this connection to imprecise probability actually helps a lot. So the way I think of this and the way I talk to my students in class is I say, p-values, they measure plausibility of the null hypothesis. And I tell them that confidence regions are just collections of plausible values. And I can use that term plausible because I know that that's actually correct. It's not like I'm just assigning these new words. It's that there is an imprecise probability connection between these things. And so it is right to call this thing, call p-values plausibility. And it's right to think of confidence in terms of plausibility. This is the right, in my opinion, is the right way to do it. And it comes from this being a very natural way of expressing what those frequentist things are doing. So I like this here. So this was so I teach this stuff of plausibility to the students in my class. I don't really tell them what imprecise probability is. I maybe say a few words about this, but they basically know nothing about imprecise probability. And so here is a message that a student sent to me sort of after the class was over to kind of say how using this notion of plausibility to explain p-values was actually very helpful for them and actually helped them to get a job. So I don't know if every student has that experience. Probably not, but I thought that this was a nice indication that there's something of value here that's like not just about the mathematics, it's about how do we communicate things. And I think the imprecise probability angle is actually quite nice. It's really impossible to think of p-values and confidence in terms of probabilities, at least not in a correct way. But this is a very natural way to interpret them, and it's actually it is the right way mathematically too. So what I've shown you so far was basically where if I take something that if I take some kind of a frequentist procedure like a p-value or a confidence interval, then we can just from that we can construct this valid IM that has this possibility measure type of structure just by kind of employing this coverage plus consonance strategy. So that kind of makes it seem as if p-values and confidence are sort of their own things, and then you embellish them by adding this kind of consonance to it, and then only through this embellishment that you can get to the imprecise probability connection. So there's actually more that we can say. And so this is, I have a somewhat complicated looking slide coming next, but I'll try to explain what's going on here. So this is a sort of a formal result that I'm being not quite so, I'm being a little bit vague about, and we'll revisit later when we have all the pieces in place to understand what's going on. Okay, so I apologize in advance for having so much stuff on this slide, but it makes sense to put it all on one slide and then try to explain. So I want to start with here some family of confidence regions. So there's a C alpha, and this is indexed by this alpha parameter, basically the confidence level. So these are confidence regions for a feature of the full parameter. So it's like a good example of this is if you have a normal distribution problem, there's a mean and there's a variance. So we know that we know how to use the t-test or sort of t-statistic to calculate a confidence interval for the mean, right? So this is I've kind of done this marginalization and say I've come up with some confidence regions that are for that feature alone, not directly about the full model parameter. Okay, and so what this is supposed to satisfy is a few things. One is that it satisfies this coverage condition. So what this means is that if I look at this probability that the confidence region contains the thing I'm trying to learn, this probability should be at least that nominal level. So when I call this a 100 times 1 minus alpha confidence region, I'm advertising that it has coverage probability at least 1 minus alpha. So I'm just saying that the advertisement has to be correct. The other thing is that there's some kind of a nestedness property that these confidence regions should be nested. And so you can maybe see what's going on here. There's some relation to what Ignacio was talking earlier about these possibility measures corresponding to things like nested random sets. And so this is all somehow kind of connected. The nestedness of these confidence regions is related to the nestedness of random sets that are behind these possibility measures. Then there's a third thing, which is about compatibility, which we don't really have terminology to explain. It's a technical condition that, as far as I know, is easy to be satisfied, or relatively mild, kind of an assumption, but I'm not going to say anything about that now. I can say a few more words about it later. So anyways, I have confidence region that satisfy these properties. So things like that T distribution confidence intervals we talked about before would satisfy all of these. So what the theorem says is that, so I start with this confidence region, then there exists this valid inferential model, and this is a valid inferential model for the full parameter. Okay, so this is not the same as just sort of directly doing the construction using the p-value and consonance on the confidence region from just about this one. So this is a valid inferential model about the full model parameter. And it's determined by consonance and that kind of that contour function. So this is a bit more structure in this in the formal result than what I'm seeing here. So there is such a thing. This is a function that's on the full parameter space, such that if I do this sort of marginalization to the phi parameter, this interest parameter here. So I do that marginalization, and then I construct a new, this is a new confidence interval. So this one is done by first doing the optimization of that pi function and then cutting it off at alpha. So only keeping those values of phi that have this supremum at least alpha. So now I have two confidence regions in play. One is the C alpha and one is the C alpha star. The C alpha star is the one that's constructed based on this valid inferential model and the consonants and the contour function. So then the end is that there's a relationship between those two confidence regions, and the relationship is here. It says that the C alpha is never bigger than this, or C alpha star is never bigger than the C alpha. It's contained in there. Sometimes it's a proper subset, other times they're actually the same. But the theory says that you'll never have a bigger region coming out of this.
So,
Okay.
sorry, Ryan.
Sure.
Can I ask about the nested property? Because
Sure.
I find it counterintuitive when beta is greater than alpha. Shouldn't the confidence region of beta include the confidence region of alpha? Shouldn't it be the other way around?
Well, let's try and check my work here. So it's possible I wrote it wrong. So let's say alpha is 0.5 and beta is 0.1. So it's like, then we'd be talking about a 95% confidence region versus a 90%.
Right. So if alpha is 0.5 and beta is 0.1, then the inequality is flipped up, right? So it would be beta would be less than alpha then.
But a 90% confidence region is smaller than a 95.
Right. Okay.
Yeah. So I think this is right. So if beta was 0.1 and alpha was 0.05, then C beta is a 90% confidence region and C alpha is 95.
Right. So the inequality should be flipped, right? So beta is less than alpha, right?
No.
Because beta is 0.1 and alpha is 0.5, so beta is less than alpha, right? So this inequality
I think I
applies.
said it wrong. It's 0.05, 0.05 and 0.1. So 0.05 is less than 0.1. And so then we'd be talking about a 90% interval here and a 95% interval here. So the 90% interval is smaller than the 95%.
Okay.
Right. So it's like the more confident you have to be, the bigger the set has to be.
Sure.
Is that right?
Okay.
Is that okay?
Yes, I think so.
Okay. So sorry, is it okay, or do you want me to explain again?
I guess okay, so you mean 0.1 and 0.05. Yeah, okay, in that case.
So I mean, this is standard, but it is it's sort of confusing because we index it by alpha, but then we call them 95, like we would call it a 95% interval, but it's really is, I mean, maybe better should be one, the index here should be 1 minus alpha, so that like you would think.
Okay, yeah.
I think that's probably what's the issue.
Okay, no, thanks. Sorry.
Okay, so all right, so I see a question here about from Dominic. This is actually a good question. I really have no idea. So if that were true, that would be pretty awesome. I don't know. So if that's true and I'm just not aware of it, I'd be very happy to know more about this kind of connection. Okay, so so here's I guess the main conclusion here is that I can start with something that's a very reasonable kind of frequentist procedure, has coverage probability guarantees, has this kind of nestedness property, and this compatibility is related to the extra structure that I'm not telling you about here. But it says that we know how to construct some new confidence region that's no bigger than the original one. So I can either reproduce that original thing, or I can actually do better. So the paper actually says there's a parallel result that's given there is about doing the same kind of thing, but now not for confidence regions, but for tests. So if you have a testing procedure, I can do the same thing. So test about some phi parameter, I can convert that into a valid inferential model on the full parameter space whose corresponding test is no less powerful than the original one. So I mentioned already compatibility has something to do with some of the structure that we'll talk about in part 2. So here, I guess, is the maybe sort of takeaway things is that, right, so that that connection to the, that connection between the frequentist procedures and the imprecise probability, I think, is not an embellishment. It's that those things are actually already inside of there. And so what this theorem is kind of doing is kind of identifying the things that are already inside of there, and then just re-expressing that original confidence region using those plausibility related things that are already built in. This also shows that, like I was claiming, is that the plausibility is really the right way to think about these p-values, I think, both intuitively and mathematically. And that actually anything that you can think of that's a good procedure, like good statistical procedure, like any kind of test that's has this type 1 error control, any kind of confidence region that satisfies this coverage probability condition, that all of those things correspond to valid IMs. And they actually, more than just this kind of plausibility function sort of notion that I described here, there's actually more structure inside of these, the valid IMs that come out of this construction. And finally, it's not really clear why this matters at the moment, but actually the proof of the theorem is done by actually doing the construction. So you find something that has this structure I'll talk about next time, and then show that it's through this kind of construction, you can get some intervals, say confidence regions that are more efficient than the one that you started with. So it's still valid, means that the coverage probability is right, but being smaller means that it's more efficient. So actually, because the proof is constructive, you can just you can use this construction to actually take something that is given and actually come up with something that's better, more efficient. So I'll show you something about how you can actually treat this as this proof is kind of like an algorithm for constructing new procedures that are more efficient than the ones that you used to start with. So there's a question here. So Dominic's question about in the normal distribution example, is it the case that confidence about the mean and variance, the normal distribution constructed from them? Yes, I believe that is, I believe that that's correct. So the normal distribution is a special one because of the, largely because of the symmetry. So it's not really the variance part, but that there's kind of a symmetric role played by the data part and the parameter part. And so you, just by kind of swapping their, the roles, you maintain the same kind of a shape. And well, I mean, there's, I guess, a couple of things going on, but it's mainly the location structure and the, so if you're familiar with some of the Bayesian work, what it has to do with like non-informative prior distributions, the Bayesian's non-informative prior distribution. So the prior that you have to take is one that's a constant. Just means that it's like your prior density is just equal to 1. It's there's no shape to it. So with this, it actually corresponds to the confidence distribution, and explains this kind of just swapping the role that the theta and the mean and the y play. So I'm not sure if this exactly is the answering the question, but it's because of it's because of the fact that the parameter, in this case, the mean of a normal, is a location parameter, and location parameters there's some extra structure that's there. And so ultimately the confidence distribution or fiducial distribution, whatever you want to call it, is just amounts to swapping the role played by the data part and the location parameter part. And so this is a way you can get to the confidence distributions. That's right. Yeah. So if there's no symmetry, then there may be other ways to do it, but generally you can't, if without the symmetry, you can't construct a confidence distribution or like a Bayesian kind of posterior distribution that will kind of exactly achieve things like give you confidence regions that have these desired properties. So the symmetry is actually very important for being able to preserve the statistical properties, but these are properties about the intervals that are derived from the distribution, not in terms of validity. So validity is actually stronger. Yeah. Okay, good. Yeah. So I glad I understood. All right, so then I'll talk more later about kind of consequences of the constructive nature of the proof that gives us some ways to actually construct new procedures that are better than the original in some cases. All right, so then I guess I'm basically ready to wrap up for the first part. So so this is just kind of a review of what we said. So this notion of inferential model, this is just some kind of a general construct that's to be used for probabilistic inference. And so then what we say is that, well, if I want these inferential models to be reliable, then I need to satisfy some kind of property. And so the property that I proposed here was this validity property. And then it says, well, okay, if I want to achieve this validity property, then what kind of structure, like what kind of mathematical properties should that probabilistic inference, that capacity, that's output, what kind of properties should that satisfy? And so what turned out is that by false confidence theorem says there's no probability can't do it, but that at least it is possible to construct a consonant plausibility or a possibility measure that can achieve it. So I think this is interesting. I can't say I've seen anything about this before that, so the imprecise probability thing is showing up here, not because we're treating the statistical model as somehow as having some imprecision in it. It's that the imprecision is coming because it's necessary to have reliable statistical inference. So that I think is I've not seen any observations like that before. So I think that's actually important. And I'm sort of thinking that there must be some new opportunities for, I guess, imprecise probability community in this context. It's that it's not necessarily that we're starting with imprecise models and then trying to build this imprecision into the statistical methods. It's that the imprecision is already there. You have to have this imprecision if you're going to produce some reliable statistical methods, at least in the sense of the validity property I was defining here. So what I wanted to do, so what I hope is that after part one, what I was trying to do was to motivate sort of why we want to do this, why we want to get something that looks like this particular kind of imprecise probability for statistical inference. So I showed you that here by basically reverse engineering this imprecise probability from a more familiar kind of a statistical method, like p-values for a test or confidence regions. But there's no reason that you have to start with one of those things to get to this. So what I want to talk about in part two, this is sort of how do you just directly construct these things. So at the time, I think when we started doing this, we didn't know really about this, like the construction that I showed you here. So about kind of taking that p-values or whatever and then converting it using this coverage plus consonants type of strategy to produce this valid IM. I don't think we knew about that at the time. What we were doing was kind of thinking about sort of what's a way to set this up so that I can be sure in the end that I will have a inferential model that achieves this validity property. So that's what was in that's what the book is about, is kind of how do you do this kind of construction to achieve validity. So what I'll do next time is kind of talk about how do we do that construction. I'll show you some more examples. Today was pretty high level in terms of just trying to convince you that this is a reasonable approach to take. But we'll talk about a few more examples next time, and then validity I think is definitely is important, but validity alone doesn't mean it's actually a good procedure. So we have to think about sort of a secondary condition, which is what's called efficiency, and I'll talk about how do we try to achieve this efficiency and validity simultaneously. So Marco, I have a few minutes still, right?
Yeah, we have a few minutes, so I mean, we can, if you want, we can leave it for questions. This 10 minutes.
But I do have a couple of more like things that I was sort of saving if it was kind of optional.
Sure,
so
sure.
we have a few minutes. I'll say them.
Yeah. Sure.
Okay, so I have a few things that are sort of preachy, so I wasn't sure I was going to actually do them, but if we have a few minutes, I can do it. So. I guess Michael and Scott also maybe know something about this. Obviously, we don't get necessarily friendly feedback about the work on false confidence. It's actually, I mean, it's actually making very bold claims, is that efforts to kind of do these constructions using additive probabilities actually can't work. So, you know, a very natural thing is like, so why do we care about this, right? You somehow, is it just set up so that you can make such a strong claim? So what the false confidence theorem, remember what it says is that, you know, it's basically that there will be assertions such that the additive probability will tend to assign them high belief. So it doesn't mean that like the assertion that you are specifically interested in is going to be problematic. It just says that there are bad assertions, right? That these problematic assertions are there. So there's a risk. It's not somehow a guarantee that something will go wrong, but there is a risk. You know, if one is a statistician that's like directly working on the you know, in the application and doing the data analysis, they may have the sort of skills and experience to recognize, okay, something's maybe potentially bad, and they can somehow manage these risks, so that they would recognize, okay, I can't just take this, I can't use this statistical method and plug in any kind of assertion that I want, because there's some risk, right? So they can manage this, I think, reasonably well. However, I think, I mean, I can speak from my experience in you know, as an academic statistician, is that most of us, and in fact, I think we're largely incentivized to be in the job of developing the methods and software that other people are going to use. So whatever experience and expertise that I have that might help me to manage that risk is not being answered to the people who are actually going to be doing it, because I'm the one that's going to be building these methods in the software, and someone else is going to be using them. So the only way that I can somehow manage this risk from this kind of detached role would be, I think, two things. One is either I can say, here are the hypotheses that are potentially dangerous, or I can give them some methods that can avoid the false confidence altogether. So that, to me, is the kind of the point of this, is that unless I'm really engaged into this like applied problem and I'm doing the data analysis, I can't be sure that these risks aren't real. So then the only thing I can do is kind of put on the box of, you know, when someone goes to the shelf to take these methods down, on the box there it says you can use this for this hypothesis and this hypothesis, but not for these. Right? Either that, or we give them a tool inside that box that just can't suffer from false confidence. I think a legitimate question, I mean, definitely is a legitimate question, and I'll talk more about this in the part 3, is like, why should we really care about all the assertions? So in the definition of validity, actually quite strong, it says that we require this kind of a calibration for every hypothesis, every assertion. So this is again back to that kind of the risk in the false confidence, is that, you know, there are going to be some of these assertions that are bad. And so by sort of requiring validity, you know, that validity requires this kind of calibration for all of the assertions is a strong way to protect against that kind of risk. So naturally, I think many statisticians who have seen this would sort of respond and say, well, these, you know, I don't care about those challenging assertions. They're not practical ones. So I think in some sense I can respect that, although we have examples like in the satellite collision example where that is definitely a practical assertion, and there's something seriously that's gone wrong. I think, I mean, I approach this more from like a foundational perspective, and that is that it's these challenging ones that are actually the most important, because they sort of shed light on what's actually going on, what's the structure about these problems that makes them challenging. It's like, not by just looking at the easy parts can we identify what are sort of the key questions. So I like this kind of analogy I thought of, was like, I mean, you know, measurability is kind of an odd thing. And so the reason why mathematicians actually can understand and appreciate what measurability gives you is that they've actually thought about non-measurable things and how problematic those can be. So I think it's the same kind of thing here, is if you just dismiss the things that are complicated as impractical, then you may never really understand the practical parts of it. And finally, just the last thing here is about this validity property and sort of what's the cost, right? So I'm setting kind of a high bar that says, okay, we want to be able to achieve this validity property. So what are we giving up? So the main thing here is that validity requires some kind of conservatism. So if I insist on this validity property being satisfied for all assertions, then there's going to be potentially many assertions about which my inferences are conservative. I don't actually think this is a bad thing. I think that maybe we tend to exaggerate how informative data is. And so we're maybe think that we're able to say more than we really can. So I thought of another sort of analogy here is that, if I'm concerned about not being wrong, then I can't use the same level of precision to answer questions, all possible questions. So there's certain questions I might be able to answer with high degree of certainty or precision, and other things maybe not. So statistics I know a bit about, so I can answer with some precision, but if you ask me questions about zoology or physics or something, I may not be able to. So what I need is that if I'm concerned about potentially being wrong, then I need to be able to say, I don't know. And so it's this I don't know that's kind of related to the non-additivity and the conservatism that comes in this imprecise probability framework. So that doesn't mean that efficiency is important, and I'll talk about the efficiency side tomorrow. All right, so that was all I had for part one. So we'll pick up, I guess, obviously if there's questions, happy to continue to talk, but yeah, tomorrow we'll pick up in the morning for me, about the construction. How do we directly construct these valid inferential models?
Okay, thank you so much, and let's give a round of applause to Ryan for this.
Okay, thank you.
Thanks so much.
It's a really insightful, excellent lecture, and looking forward for tomorrow, of course. So we have, if we have questions, I would just ask you to unmute and jump in. I think we can manage that.
Yeah, please, if there are any questions.
I have a question, if that's all right.
Sure.
So it was really nice presentation, right? And I really found it very insightful and very thought-provoking. If I understand that main message is that you found a way to produce valid, I mean, first of all, you identified an issue with inferential models that not many people are maybe as aware of as they should be, which is really great. And then you found a way to produce valid inferential models based on kind of frequentist ideas with an imprecise flavor put on top of it to fix those issues. And I'm wondering if you can do the same thing. Could you like give other standard inferential models a similar treatment? Is there kind of a general way of doing that? Like say you have a Bayesian inference procedure, or more generally maybe some imprecise even inference procedures that may not satisfy validity. Is there a way of like a general fix for that based on the ideas that you've had?
Well, I guess so. Maybe one thing I guess it's related to this question. I should maybe I can share again. So inside of here, this is maybe not exactly what you were asking about, but I guess one thing I maybe should clarify is that while this family of confidence regions that I'm starting with, I mean, it's supposed to have these properties, but there's nothing that says this can't be based on some kind of a Bayesian approach.
Right. Okay.
So yeah. This can be, if you're able to start with something Bayesian and satisfy conditions,
yes,
then this still applies. And so there's also no reason that if this came from maybe something that's like using some imprecise probability model, right? So if you were able to, so all that matters is that it has these properties.
Yes, so I think the coverage is normally an issue. I would think that might be an issue because you're looking at you're looking at a posterior, right? To get credible, like they can't be credible intervals because credible intervals don't satisfy coverage. But that is essential, I guess. Or right.
Yeah.
Okay. Yeah, but thanks for pointing that out.
Right.
Yeah.
I mean, yeah, I don't know if I was planning to mention this in the third lecture, but something that I guess most statistical methods have something like this, but it's not like for every fixed sample size, say. So if maybe you were dealing with IID samples, that you could achieve something like this in most cases with like n going to infinity.
Yeah.
So something that I'm not really sure about is, so let's say I start with, for example, maybe I construct my confidence interval based on like central limit theorem type of approximation. So that would be that would end up having this kind of coverage probability properties kind of in a limit.
Yes, that's right. That's right. So yeah. So yeah.
So what would happen, for example, if you kind of tried to use some of this machinery on something that's not exactly valid, but only approximately so? Like, does something about this kind of improve things? That I don't know. So I think that maybe was what you were asking about.
Yes, well, I think that's the whole thing about kind of Bayesian procedures, is that some theta values you don't care because they have such a low prior probability, and you kind of believe your prior. So you wouldn't take. That's why you don't take you don't construct them in the same way. You don't have this optimization in the same way appearing as you have with frequentist procedures. Right, yeah. Okay, but thanks for that. Was really really helpful.
Okay.
Thanks.
Thanks.
Yeah, thanks.
So I'll jump in if nobody else is champing up a bit. Teddy Seinfeld sort of famously showed us that insisting on precise probabilities makes us give up democracy, which is the way I like to say it. And I know that Fisher's fascistic background, maybe he's okay with that. But I find it hard to believe that he would be willing to give up validity. Is there a realm in which Fisher or anybody serious about these issues would care to, give up validity? Do you not think that that really is as important as anything in inference? Or
I do. I mean, that's basically what I'm pushing here. I think where Fisher had I don't necessarily want to call it a slip, but I think what Fisher didn't anticipate was that you can do this construction and have these good properties, say, on certain assertions, but that they don't hold.
Right.
You do things like to marginalize or kind of propagate things through. So it really, that's where you end up getting, where you need this the imprecise probability results, because it's basically you're swapping some kind of integration with this optimization, and the optimization preserves the properties. And in Fisher's time, these ideas really weren't there. So like they maybe sort of existed, but they weren't sort of, I guess, what typical statisticians would know anything about. So I think that he was really trying to do this using probability, not because that's what he really thought was right. That was maybe the only thing he knew.
Only thing around, yeah.
It's like the only thing out. So like it's like there's that law of a hammer. So it's like if you only have a hammer, then everything looks like a nail. Right?
So I show the Michael's thing about the satellite conjunction to colleagues here at Liverpool, including colleagues who work in satellite conjunction, and they are remarkably blasé about it. I think they'll be blasé until those satellites that Tesla, like 100 and some satellites he threw up into the into the orbit just a few days ago, until those start colliding with something, they'll be blasé, right? But my question is the argument is, well, we wouldn't have done the analysis that way, and it seems to me that the only reason we know about dilution is because they did the analysis that way. But so is there a way that probabilists can protect themselves from things like probability dilution other than going to an approach such as you advocate? Can they do anything else?
I mean, I think what you can, so there is one way, and I don't know exactly what I was planning to say on tomorrow, but I mean, if you really have like legitimate prior information, then you can essentially rule out certain things, because if you really believe in that prior distribution, then you can achieve something kind of like this validity property. It's a weaker version, but you can achieve that if the prior information you have is genuine, that you actually believe that this is sort of a description of uncertainty in the parameter. So for example, like sets that you would assign small prior probability to really can't happen. So if you have this kind of setup, then there is a way that you can achieve something like validity in a Bayesian way, where you actually can use additive measures. But if you get to this situation where there are certain values of the parameter, and you really can't say that like these ones you can rule them out, or that you can assign them sort of exactly like 0 or very small kind of prior probabilities and then effectively ignore them. If you don't have that kind of information, then taking like a prior distribution that's flat, for example, that's a kind of a standard thing that one does. If you're unsure about the prior distribution, you do something which is basically flat. What this is effectively doing, and this is a way to understand actually what's going on in that satellite problem, is that it's effectively a Bayesian solution based on a flat prior. And so then if you say, well, the data is not very informative, you have high noise in the data, then it's what this Bayesian solution will do is revert back to prior. But the prior is not a meaningful one. You just put it there because you were trying to use the Bayesian machine. So then that flat prior spreads its mass all around. And that's why it decides that the non-collision event gets high probability, because the prior says non-collision has high probability.
So that suggests if you can always restrict yourself to using highly informative priors, you might escape problems like that anyway.
Yeah.
Okay.
But I think, I mean, if having highly informative priors was the norm, then we wouldn't be talking about frequentist things.
For sure. But the Bayesians are going to say, "Yeah, I told you so."
Yeah.
Use your priors.
Yeah.
Okay. Thanks.
Sure.
I guess an extension to that question then, Ryan, is, are there other model constructions that you should be aware of this kind of thing happening from the get-go? So if you see non-informative priors, that might be a warning sign. Are there other things that the modeler should at least be aware of?
Let's see. So this is something I don't have an answer for, but this is my hunch. So I can share you that with the caveat that this is just a hunch or maybe an educated guess. I think that the challenging cases will arise when the thing you're interested in it's of this kind of setting, where there's maybe some kind of full model parameter. You're interested in some low dimensional feature, and specifically that low dimensional feature is highly nonlinear in the original parameter. So, and as an example where you normally wouldn't see an issue is, let's say it's that normal distribution problem. I have a mean invariance, mu sigma squared. And then if what I'm interested in is mu, the mean. So this would be a very nice linear function of that pair mu sigma, just throw away the sigma and keep the mu. So that one would be one where things generally would be fine. I say generally fine, not in the sense that you achieve validity in my sense, but that Bayesian procedures that would give you, basically any kind of reasonable prior distribution would, after so much data, give you very good answers about the mean. Where you get into trouble is when that feature is not linear. So this Feller-Creasy problem was one very nonlinear. It's the ratio. The satellite collision corresponds to something which is basically, I have a vector of thetas, and what I care about is the norm of that vector. So it's like you square and then you square root. So it's this also kind of a nonlinear function. So my guess is that where you see these problems arise, and they're sort of most extreme, is when this feature you care about is a highly nonlinear function of the full parameter. So that's I think the best that I can say.
Nearly any problem that's interesting.
Yeah, I don't think it has anything to do with the model itself. So
Okay.
that I can't say that that's correct, but my
Sure.
point now is that it's not so much about the model itself. It's about how nonlinear this feature of interest is as a function of the full parameter.
That's really interesting. Thank you.
Yeah. So I mean, this is, there's a kind of a class of examples that includes things like problems with measurement error. So like regression problems where you have error in both Y and X. And then maybe you're interested in, say, you know, so you care about the actual parameters for the unobserved value of the covariate. And so when you have measurement error in the covariate, that kind of confounds things. And so then it turns, ultimately, I mean, I can't just say it in words here, but it turns things into something very much like this Feller-Creasy example. So there's a class of problems that are, we can jump to it here. So I do have the label of this class later on. It would be hard to understand if I just say the words. So yeah. So actually, this is my slide about that. So there's this very nice paper, Glesser and Huang, 1987. So they talk there about this special class of problems for which there are no bounded, let me say it the other way, that if you find any kind of a, call it quote, confidence interval that has finite length with positive probability, like for every value of the parameters, then this actually has coverage probability 0. So there's actually very extreme kind of things that can happen when you're in these certain problems where the parameters is like the interest parameter is very nonlinear in the full parameter. And my feeling is that this is very closely related to what's going on. This false confidence is very closely related to what's going on in the Glesser-Huang paper. I've not put the details together yet, but I think that there's something going on there. So Don Fraser also talks about this in his 2011 paper about nonlinearity and the effect that this has on the like how well a Bayesian posterior can approximate confidence. And so for very nonlinear functions, the approximation can be quite bad, but more closer to linear type of feature parameters, the Bayesian approximation is better. So I kind of think that that's kind of like, it's sort of on a spectrum, and there's at some point where it's kind of like, well, too nonlinear, and then the like validity type of properties would break down. And that's where the false confidence would show up.
All right, will your slides be available? I didn't see them in what Marco sent.
I put them in the share. They're on my website. So if you if you can find the website, they're there. I think I did put them in the chat just before I started.
I also added to the program, to the Google Doc.
Okay, thanks.
It's okay, Ryan, if I add the link to the slides and
Yeah, no problem.
So I guess, should we come to a close now?
Yeah, sounds good.
Okay, thanks, Matthias, for coming.
Okay, yeah, great. Yeah, thanks everybody. So I guess I'll be back tomorrow morning.
Yes, for you will be early morning.
It's not so early, but it's fine.
Well, thanks. Thanks again. Yes. Yes, round of applause. Oh. It's like the differential. Everyone at their own time. But yeah, thank you so much. And so yeah, we'll close here and we'll meet again tomorrow.
Okay, great. Yeah, see you tomorrow.